Hello, um, this is Jangho Park, and I collaborated with Chenyu. Our project is called cat, cat detection using deep reinforcement learning. This project aims to actively detect the cat in the image using deep reinforcement learning. The Q network is trained so that the agent can use this as an optimal policy to localize a cat in the image. As you can see here, our goal is to find the cat region in the input image. This is one of the results of my model. Yes, localization of a cat in the image is a goal. Here is the basic procedure. As you can see here, there are a bunch of states and actions. Let me explain from the left to the right. As you can see in the left, the region shows the cow, but cow is very small. In order to localize a cow well, we have to shrink the box so that it contains the cow as much as possible. So there are a bunch of actions to localize a cow in the image. As you can see here from the right side of the result, in this case, the cow is localized. Our project is to find the cat rather than cow. So our test set and training set are cat images, not cow images. The agent basically starts with a rectangular box in the given image. That given image is an environment. And the agent manipulates the box so that it contains a cat in the image. There are 9 actions for manipulation. You can see the below image. Horizontal moves, vertical moves, scale changes, aspect ratio changes, and the trigger. Trigger means our localization task is done. I borrowed this figure from the Joan. In deep reinforcement learning, it is very important to design reward function. Reward is based on intersection of a union between the ground truth region and agent's box. If the action of the agents is effective, the agents get reward, such as +1. Otherwise, -1. This reward design leads the agent to manipulate the box in a way that maximizes the sum of the rewards received during an interaction with the environment. As I mentioned before, trigger means the end. In this case, if IOU increased by a certain amount, let's say threshold 0.6, the agent will get a big reward, +3, otherwise -3. Then why Q networks is needed? Since there are infinitely many states, it is almost impossible to use classical Q learning algorithms. Therefore, I used deep Q network. Since our goal is to fit image region to the network as a state and get 9 different Q values for the state, I used the well-known pre-trained VGG16 as a feature extractor to deal with an input region. And this region is fed into our Q network. Note that the input region of the agent must be warped into a 224 by 224 image, and this goes into the pre-trained VGG16. I follow the deep Q learning algorithm proposed by him. This approach estimates action value function using a neural net. You can check the diagram below. Input region is warped into the 224 by 224 pixel image, and this is fed into the 5 convolution layers, and after that the vectors are flattened so that it can be fed into the deep Q network. There are 9 actions, 9 outputs here. Input region is warped image, and pre-trained CNN is VG16, as I mentioned before. I also want to thank you to the Juan for this figure. Okay, let's dive into the code right now. I use the PyTorch as a deep learning framework. Before that, we have to load the pre-trained VG16 model and use it as a feature extractor. As you can see here, I downloaded the VGG16 model, pre-trained model, and load into the VGG16 class object. And VGG16.eval means it is only used to inference, not train. Okay, I freeze all weights because VG16 will be used for feature extractor. Here is VGG16. There are several utility functions. The first one is crop warp image. This crops image so that the cropped one is of size 3 by 224 by 224. Note that 3 means 3 channels RGB. Extract feature from VGG16 means it extracts features from the cropped region using pre-trained VGG16. Here is the detail. And it is very important to prepare the dataset before we train the model. So I created my own personal dataset class here. This class is a subclass of a dataset, and dataset is a class from PyTorch. Oh, I didn't mention the VOG 2012, which is a dataset for our job. Here's the detail. And next one is I define the DeepQ network like this. It is just a simple fully connected layers, simple neural net, as you can see here. The input dimension is this, and the output dimension is 9. I use the dropout layer to avoid overfitting. I created my dataset from the given path. I used cat images, and this is a transform function so that it is normalized. Here's the utility function, and here is also the utility function. I borrowed the source code from this link. It calculates the intersection over union given two regions. The important thing, I created my own environment class, which is very convenient when I train the deep reinforced DeepQ network. Here is the image environment class, and it has render class to check whether I'm doing good or not, and get state returns our current state, and step means moves the agent according to the action vector. One hot means that it is a one hot encoding vector, which means only one element of 9 is 1. Here are the 9 different actions, and it manipulates the region. These coordinates are the coordinates of regions. You can see here that if action is triggered, if current IO is better than previous IO by amount of 0.6, reward is very big, very large, 3.0. Otherwise, penalize the agent by -3. And here is the normal. Here is the reward for normal actions. If it improves, reward is +1, otherwise -1. This is a training task. The replay train function trains our main DQN using a batch input. Why is it called replay? Because we use replay history memory to make learning faster. Here is the learning step. As you can see here, I used smooth Allen laws, and this is the optimizer stochastic gradient descent method. And loss is here, and loss.backward optimizer step trains the network, trains the main DQN network. And here is the main function, very important stuff. I prepared a total of 5 to 9 CAD images, and 480 images are used to train the network, and the remaining images are used to evaluate the network. Here is the hyperparameter, and there are two different DeepQ network. This is a policy network, and this is for training target network. Before that, load all states from main DQN to target DQN. Here is the learning folder. For each episode, agents take actions and learn and record history. As you can see here, this part saves the experience. And I mentioned before the replay buffer. We record every history to replay buffer so that it can be used to train our main DQN. For every 10 episodes, we train main DQN. Here is the training part. We sample 10 examples from replay buffer and make them as a mini batch and train the main DQN using the mini batch. In order to save the model, I call the torch.save function. And finally, target DQN must be the same as main DQN after training. This is the thing As you can see here, here is our training step for all episodes, training episodes. After training, we have to evaluate. Here. Note that 39 images are used to evaluate the agent's performance. You can see the localized CAD regions in the test set below. You can see here, this works well, this works poor, this works quite well, quite well, quite well, quite well, quite well. This worked quite well as well, but this is not good. This is good. Oh, actually, the agent thinks that this is a cat, and this works well. This works quite well. Little bit bad. Work well, something like that. Yeah, works well. Works well. Works well. Works well. Works bad. Works well. Works well. Yeah. These are the results. Works well. My conclusion is that, as you can see above, the agent shows pretty decent performance. However, there are still some bad results. I think there are several reasons for that. The first one is the number of CAD images we prepare for training is quite low. We have to gather more and more CAD images to make the agent do the right things. And the second thing is that there are lots of hyperparameters to choose to optimize the result. For example, let's say if our reward design is bad, the result would be bad, and there is a discount factor which is 0.99 in this case, and there is also a Q network architecture design choice, and etc. Okay, thank you. This is the end of my presentation, and as I mentioned before, I collaborate with Chenyu Shi, and he's going to tell you about the different approach to do the same thing. He also do the deep. He also used the deep Q network, but his action state space are different from me, and also mm, um, I mentioned here. Okay, Chenyu Shi tried to solve the same problem, but as I mentioned before, different approach. The agent has 9 actions, whereas my agent has 9 different. Oh, sorry, it's a typo. He has actually 6 different actions. Yeah. His approach is called hierarchical object detection, which is very different from me. I manipulate the boxes itself, but hierarchical object detection is very different. For the details, you can check his report as well as his presentation. He's now going to tell you about how he did. Thank you.
Hello everyone, my name is Chen Yuxi and I'm gonna talk about my part of our project. Our project name is Cat Detection Use Deep Reinforcement Learning. So the basic idea for our project is like using a reinforcement learning idea to achieve object detection tasks. So the difference between my work and my teammates' work is like we are using actually different searching strategy. Mine is hierarchical searching. So firstly, let me talk about the data process. We are using VOC 2012 for model training, and actually I load the image data and the annotation data into a data object, and you can see it here is the one data point of the data object. The image is the image of the is a one image, and the annotation of that image is like a list of annotation, list of dictionary, and each dictionary represent one object within that image. You can see it here is a class name, and its gratuitous boundary. Since we only want to find cat within images, so I wrote a field by class method to fill out the images which contains cat. So after we do the filtering, there are only 1000 pictures left. Then I'm gonna talk about the reinforcement learning part. So actually we are training an agent which can perform object searching behavior. So the agent is very like human. When people locate an object within an image, we like to tend to focus firstly on the most salient part, and then we do a top-down scale search. And our agent also have the same strategy. The actions of our agent, there are totally 6 actions, and there is 5 possible movements for our actions. The movements means that the actions will move the image window to scale it down and to a smaller sub window, and there is 5 directions to move the sub window. Is up left, up right, down left, down right, and the center. And the final actions is a terminal trigger action, which indicates the search has finished and the object has been found. So we also record a history vector, which contains the last 4 actions the agent has taken, and the history vector is part of our state feature. So to represent the current state of our agent, we need to know that the agent is based on one image. So one agent is responsible for find images, cat within one image. So the state of our agent is the image window of our agent and the history vector of our agent. To represent the image window, like the subregion of the image, we need a pre-trained computer vision model to generate a image descriptor. So for this part, we are using VGG16 CN block to output an image descriptor, and then we can concatenate the image descriptor with the agent history movement as a state feature to represent the state. And then we need to determine if the movement is good or not. So we are using IOU to represent as a metric for our agent's behavior. So the IOU is very simple. It's the area of overlap divided by the area of union. So it's kind of represents the overlap between the ground truth boundary box with the current subregion of our image window. So the reward is very easy to calculate. When the IOU increase, we like give the agent a bonus. When the IOU increase because of the movement, we will give the agent a punishment. And the value of the bonus and punishment is different between the movement actions and the terminal actions, because we need to assign a bigger bonus or punishment for the terminal actions to let the agent terminate the searching process on to choose to terminate it or not. So how does the agent choose the next actions? Actually, the agent chooses the actions based on the action's Q value. So how to calculate the Q value? The Q values are predicted by the Q models. So actually, the agent will choose the action with the highest Q value based on a greedy policy. But we are using an epsilon greedy policy, which means the epsilon value at first is very large, because in the first stage our model is not well trained, so our agent will randomly pick actions, and then after the training stage goes, the epsilon will decrease to 0.1. At that time, the agent will more likely to choose actions based on the Q values. So how to train our models? So objective function for our deep Q learning model is the MSE loss between the Q value predicted by our DQN model and the Q value calculated from the former states. We can actually calculate Q value from based on the Bellman equations, and here is the Q value of current state and actions, and here is the Q value of the last state, the past state and their actions, and there is a gamma. The gamma is like a discount factor which considers the trade-off between the immediate reward and the future reward. So if the gamma is set to 0, the agent will tend to choose the movement which will largest the next IOU, but we will have the probability to like fall into a local optimum, which means the final result might be terrible. So we need to set a reasonable discount of factors. For this project, we set that to 0.99. And when we like using to train our model with, we are using a replay memory pool to like record our state transitions. So we record one transitions as the current state, the actions and the next state and the reward. And to optimize the model, we like to select a batch from the replay memory pool, and we train our models to we're using two networkers, and the first network is a policy network. It predicts the Q value of this transition of the current status, and we are using another targeted network to calculate the expected Q value based on Bellman equations. So when we compare these two different Q values, and we calculate the loss, and we backwards on the MSE loss between the two Q values, and we can update our target network registry epoch using our policy network weights, and finally the two network will converge as the same, and after the network converges, it will predict the optimal Q value, which will make the reward largest for our agent. So here's the training loop. We set the epoch number to 50, and you can see the updated num, which represents the after each 3 epoch we will update our target network using our policy network. And the train name is that we only use part of our images as training, and we use the rest of them for model validation or for model testing. And you can see that here we set the RU threshold to 0.6, we set the gamma to 0.99, and then we begin to train the model. So for each epoch, we actually go through all images within our data object. Then we are simulate agent movement. You can see it here. We created agent at first, and for the step in the max step number, because we don't want to because we need to ensure that the agents can terminate its searching process at some point. So we set up a max step for searching. So here the agent we will calculate the current IOU of the agent, and we will record the past IOU, and we will compare these two. And if the current IOU is bigger than the threshold, we will use a terminal action. And if the IOU threshold is not reached, we will using the current state to get the next actions. Like you can see it here, we based on the policy model, and we based on the epsilon value because we are using an epsilon greedy policy. And after this step, we get some transitions, and we put our state action next state reward into our memory pool, and then we optimize our policy network using the optimized model method. Within this method, we actually do the strategy here. We randomly pick a batch from our memory pool, and we do some backwards on the loss between the Q values predicted by the policy model and the Q value calculated from the Bellman equations. And after, you can see the training logs here. And after 50 epoch, we can get a final training loss. The final training loss plot is here. You can see the loss decreased during the training stage. And then we are using object test class to predict the boundary box of cats within an image. So this is like an agent to find a cat within an image using our well-trained Q model. So you can see it here is 10 model of our test set. You can see it here. It's 10 pictures from our test set, and we are using our currently best model to train it with. You can see it here. This picture, it finds the cat, and for this picture, it also finds the cat. And there are also some bad results. You can see it here. It failed to find the cat. And here you can see the bounding boxes. So here's my work, and I hope you enjoy my video.